So today I wanted to talk to you about the Zen of Erlang, and this is something that personally took me a long time to internalize, even though I've been using the language for multiple years. And I'm sure that a lot of people here, even if you've used Erlang or stuff similar to it, with Akka, I think is the most popular in this room, you might have similar questions or similar delays in getting the core insights, I think, of the Zen of Erlang. And so one of the basic things that we get told when we start working with Erlang and the actor model and something specifically Erlang-based or similar to that is let it crash. And let it crash sounds really, really funny at first because that's the thing you want to prevent. I don't want to be actively crashing, I want the fault tolerance that comes with it. And that's a bit of a question that's super fun to have. And to me it was like saying that rocket science is about blowing stuff up. That's not really the case. If you do that, it's actually a failure. In that case, this is the RS-3 satellite, I believe. Yeah, blowing it up didn't go super well. But at the same time, if you squint right, you can say something like, well, rocket science is about harnessing the dangerous powers of explosions in a really well-controlled manner, and then it becomes a tool. And maybe that's true, maybe that's not fully true. Another way to look at it is fighting fire with fire. And there's the concept of backburning and control burns that can be used for that. In the region I come from, in Quebec, we grow a lot of blueberries, and every few years they're going to burn down the entire fields and sow them again. And the idea is that you enrich the soil by burning everything there is. And the idea of fighting forest fires, one of the things that you do is you take areas of the woodlands that are at risk of catching fire and everything, and when it's done under proper supervision, they actually burn it down to remove the ability for these kinds of risky areas to burst up in flames without control in a destructive manner. And the idea of letting it crash, I think, is deeply related to that. It's not about preventing the failures, it's about embracing them and wrapping them in such a right context that they are no longer uncontrolled destruction, but they become a powerful building block in making reliable and fault-tolerant systems. But to be able to do that, there's a few basic requirements for the recipe, a few basic ingredients. The first one of that is going to be the process. And in Erlang, the process is fully isolated. It means it's a bit of code that runs its own functionality. It is not interleaved with other ones within the same execution context. They do not share memory. And the idea is that if one of them has an error, I can take it down without impact to the others. And so it wouldn't make sense, for example, that a process doing additions and subtractions and everything like that would be killing a process maintaining database connections because their faults are entirely unrelated. So that isolation is really, really required, but you need something else. They need to be extremely lightweight. If I'm developing an object-oriented system and someone gives me a constraint such that you can only have 32 objects in your program, I'm going to tell them that they're insane, it's not useful, you cannot do something useful with only 32 objects in an object-oriented language. Similarly, in a language where what you want to do is isolate faults by processes that die independently, if you're able to only have something like 32, 60, 100 of them, it's not really good. For the simple reason that it will require me to share and to prepare all of my workloads to fit within these boundaries, and it keeps me from properly expressing the constraints of the system to be able to have them fail the way I want. And so the total isolation that we need has to be that way. And in Erlang, the processes are a bit like independent C programs. They have their own main function, and where they're done, they're done. There's nothing in there, they don't share anything. Now, of course, that's a bit like, I picked the pictures of bees for that one, for the simple reason that if you attack a beehive, bees can sting you and only the one that stung you dies. The other one don't have to die, they remain there, they survive. But similarly to bees, you need a way to communicate between your processes. Otherwise, you're just stumbling around and there's no organization possible. And so, the basic block for that is message passing. I think message passing is the most idiomatic and easy to understand mechanism that we have for any form of communication. And it needs to be asynchronous. And the reason for that comes back to whatever form of communication we had in the past, mostly sending letters to a courier that would go on a horse, go around the country, send it, and then come back. And then eventually you got something fancier, like these are Napoleonic semaphores, where you put a bunch of dudes in towers with flags, and then a bunch of dudes in other towers further away, and they just hand wave signals to each other. And that's a lot faster than having a horse cross a river. And they did that for a while, and it got replaced eventually by the telegraph, by telephones, by the internet, and blah, blah, blah. But the core of that is that all your message sending has to be asynchronous. There's nobody who goes to the post office, mails a letter, and then waits there until they get a response. And if the letter is lost, then they just die of starvation at the post office. It would be an interesting sight, but it doesn't happen. And really, it needs to be asynchronous. There's the idea that the data should be, at the very least, immutable when it is being sent. And the reason is simple, is that if I send a letter to someone, I made a photocopy, send it to someone else, it would be really, really weird that if one of the letters is destroyed, it would be destroyed for the other person. In fact, it might be even nicer to copy it, because if you do a photocopy like that, it's fully independent, and nobody has control on the destiny of the thing except the person it goes to. And so message passing is synchronous, copied is nice, and that carries very well for network semantics. And if you want to see the 8th level of the 8th circle of hell, I recommend you go read papers on distributed garbage collection. This is absolutely interesting and scary. Of course, if you send messages, you need something to receive it. And so in the case of Erlang, this is a mailbox. You've got different models in terms of Go, for example, where you have channels that can be had and channels created, might be private, might not be. But in Erlang, you work with a mailbox where all the messages are received sequentially, with the exception of a construct called the selective receive, where you're able to do message pattern matching on the messages you have and only extract some messages according to their shapes. And this turns out to be critical if you're writing any kind of complex systems. If you have a state machine with 15 states that can receive 15 events, then you're creating an event and state matrix with a 15 by 15 grid in there where all the states have to be considered if you don't want to die. If you have a selective receive, you're able to say that I am in a given state. I'm only looking at a subset of messages, and you're drastically reducing the complexity of whatever you're doing by virtue of being able to focus on only some kinds of messages. Different way to do that would have to be distinct mailboxes and everything like that, but selective receives does it very well. And so I'm able to set up processes that will communicate with each other, have discussions and everything like that. Now, this idea of having discussions is an interesting one, because if my processes are fully independent, I'm still creating this kind of shared context between processes, because if I have processes A, B, and C, and they're having a discussion and a vote in there to reach a consensus or quorum, they start having an implicit dependency on each other. And if one of them stalls, dies, disappears, or is corrupt in some way, my state is now shared in terms of the context I have, because if one of them fails, it impacts the other processes. And so we need to have a way to tie these constructs together. The idea that, yes, my process is fully independent, but the moment it starts interacting with the world and other parts of the system, I need to be able to tie that together as a unit that I want to fail as fast as possible if there's a problem. And so the two constructs we have are links and monitors. Monitors are about being a creeper. You're just staring at things, looking at them, getting a signal or a message if something goes down. And the idea is that if I'm sending a message and I'm expecting a response or something like that, I'm just tracking progress, I'm able to detect some failure in a remote process. I can do nothing about it in terms of stopping it, interrupting the execution flow of the other process, but I'm able to observe it, even if the other process died before being able to send a message. The virtual machine, the runtime environment, gives you these properties. Links are a bit different in that they're bidirectional. They go both ways, and they also carry a death sentence. If a link is triggered on one of the two processes, it sends a signal to the other one that terminates it, and then it dies. And so I picked a little picture in there of mountain climbers. And they have that little rope between them to help them survive. Now, if you did mountain climbing with Erlang and you used monitors for that, the only thing that would happen is that if someone falls down, you see them fall down and you notice it. That's great, not super useful yet. If you have links, it does the opposite of what you want. The mountain climber falls and every one of them dies. It's okay if you want to build a perfect team that never fails. If you do expect failure, it's not necessarily the best thing in the world. So what you have is a thing called the ability to trap exit. A process can mark itself as special, in which case it's able to convert an exit signal into a message it can handle, and at that point it's a bit like a monitor, even though from the other process's perspective, it's still a death sentence. And this is the basic building block that you need to build supervisors, although I'm going to come to back a bit later. But links and monitors are things that let me code into my project structure, into my code structure, the architecture, the dependencies between processes, so that if there's a fault in one of them, the others suffer the same fate. And that's about, again, having that very well-defined and self-contained unit of failure. That one is a bit entirely different, but you need preemptive scheduling. The picture there is the Apollo 11 lunar module with Neil Armstrong and Buzz Aldrin on board. Picture taken by Michael Collins, I assume, otherwise there's something really weird with NASA. In any case, when they were landing the lunar module, one of the things that they did is that they relied on the guidance, the Apollo guidance computer that they had in there. And that computer had very, very strict guidelines with NASA according to how it should be running. There were a number of CPU cycles assigned for every second or every part of operation, and all the programs running in the lunar module had to fit their share of CPU cycles. And they had other guidelines in there, such that 85% of the CPU could be used, leaving a 15% margin of error for all the things that they did. And the idea was to make sure that you don't end up overloading the CPU and having a bunch of things failing. Now, as they were going down on the moon, what happened with the guidance computer is that Buzz Aldrin and Neil Armstrong were thinking about the possibility of maybe aborting the landing phase, and then they left a radar rendezvous array up on the system. And what happened is that that one had a bug in its hardware that made it consume more cycles than it was supposed to. And as Buzz Aldrin was entering commands in the lunar module, you started getting all of these error messages in the console or whatever reporting system was there at that time, possibly blinking lights telling them that stuff was being overloaded. Now, the NASA people were not entirely crazy. They knew about these bugs, they knew about that. And in 1969, for this mission, they had programmed a priority task scheduler on the computer, which meant that if the radar stuff for rendezvous was taking too much resources and other critical stuff in there, like, I don't know, thruster control and everything, needed the resources, they could kill the task and get going. And that saved them. And that was in '69. Now, there's a lot of systems today that are written and able to do that kind of stuff and do really good stuff on only cooperative scheduling. But in '69, for life-critical systems, that was part of it. And in Erlang, it's part of one of the fundamental building blocks you have in there. And there's a few reasons for that. One of them is that I can trust library code that I install from anywhere else or something like that to never kick my system out of balance by just using too much of the CPU. The other one, and that one might be interesting for the people here who mainly use Akka and stuff like that, is the idea that I've seen about non-blocking operations. And non-blocking operations here and there, making sure that nothing stalls and everything, this is not a worry in Erlang. If I have a blocking operation that I want to block, I put it into a different process. It can block everything at once, it's going to be descheduled or something, and I'm able to do everything I want. So there is a clarity in the system you write by being able to write everything in a blocking manner. You don't need to care about yielding, you don't need to care about how long it's going to take. As long as it's in its own process, it's not going to disturb the flow of the program. That ends up being kind of critical for code clarity, preventing classes of bugs, and just overall system resilience. And the other thing that happens when you have that preemptive scheduling is that the scheduler is allowed to do fancy stuff with the metrics. So if there's a really busy process with a larger mailbox, maybe it's allowed more or fewer cycles, for example, or sending a message to that one gives you less scheduling time so that you get a kind of automated load balancing on your system. That cool plane is an F-82 Twin Mustang. And it was designed in the World War II as a long-range bomber, because other bombers were not necessarily that great at doing in great range. And the thing they did to make it work is that you had two pilots who could relay each other in their own plane. So that's really redundant hardware right in there. And network awareness is a really good thing to have. And a lot of languages and a lot of stack don't give you any of it. And it's a bit of a weird decision because every language is going to give you standard library functions to work with sockets, work with files, work with stuff like that, but very few are going to be about communicating with other devices in a way that makes sense. Being able to, for example, monitor another node, being able to monitor a remote actor or a remote endpoint that you're wanting to have. And languages like Erlang and frameworks like Akka, for example, actually provide that out of the box. And that's really a good thing to have, and you don't notice it until you don't have it anymore, but it ends up being a nice one. And so, yeah, I think that let it crash from that point of view is really about taking all these errors that we have and making them manageable. Defining well isolated units of failure, making sure that blah, 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 everything is in there. The question that comes after that is, how do you compose all of these ingredients into a recipe that makes sense? And the big structure for that, in my opinion, is the supervision tree. The idea of a supervision tree is a bit like a real tree, except it's upside down because computer scientists like to put the trunk up and the leaves down. But anyway, the idea is that everything that you have in your system that is critical, not allowed to fail, should be extremely stable, goes closer to the root of the tree, inside the trunk that doesn't move. And all the fickle parts that are allowed to fail, to crash, to do all the risky operations that are extremely moving and dangerous go into the leaves. And as most trees do, I don't know if they do it in Austin because your weather is amazing, but leaves fall down in autumn. And they go ahead and the tree survives anyway. And so it goes for supervision trees. And you've got similar construct in Akka for those who use it. But the supervisors have a really basic thing where the supervisor is on top. Using link and trapping exits, it's able to notice the death of children and restarting them or impacting them such that if the parent dies, then the children are forced to die, and you impose a hierarchy in there on the importance of your processes. The other thing that a supervisor does is that all of the processes it starts have an init function, and this init function is fully synchronous. And this is critical because when you have that synchronous function, you're able to encode guarantees about what the child should be able to provide before you actually move on. So the supervisor is going to start from the root and depth first, from left to right, and starting children. And if I'm starting a process that connects to a database and I expect the database to be there because maybe it's a local Redis instance, then it makes sense in my init function of the worker to actually start the connection to Redis. And if the connection is not able to be established, I'm communicating to my program structure that a core component expected to be there is not there anymore, and therefore I should not be able to boot until it's done. And if, on the other hand, the guarantee I give you is that I have a client for a database but necessarily connection, then I'm able to have a really, really rapid init function coming back. And I'm able to do that with all depth of the supervision tree with the idea that I set up a correct system. And so the supervisors, once they're booted, have these three broad strategies. The first one on top is 1-for-1, which means that if the second child dies, it is restarted. The implication of this strategy is that really all the children of the supervisors are independent processes. I just want them to be part of the structure. The second one is more interesting. If the second child dies, I kill both of its siblings and then bring them all back up. And the implication for that is really the one-for-all implication, meaning that there is an interdependency between all of the children. So if I'm talking about my processes A, B, and C from earlier, who were having a discussion, a chat, and a vote, and one of them dies, there's two ways forward, right? If I'm working in something like Go or C that doesn't have actual error handling, the thing I have to do is figure out that situation, either ensure that all the other peers make the right decision or try to repair the vote protocol to work only with 2 nodes or start a sibling, and that's fairly complex and error prone. The other thing I can do is just murder children and start afresh with a fresh vote. And this is a lot simpler with the assumption that I'm able to roll back to a non-stable state. If I'm rolling back to an unknown state, I'm just creating more confusion, right? You can only find your location if you're lost by knowing where you are right now. If you don't know where you are, it's impossible to find your way back anyway. So you have to restart to a non-stable state, and that comes back with the ideas of isolation in processes and message passing not being able to mutate the data you have in there. If you mutate the data and the process is handing it over to the other ones, you're going to get in trouble because you no longer have that non-stable state to roll back to. The third strategy is called RESTful 1. It's really for sequential chains of dependencies, where process number 3 depends on number 2, and number 2 depends on number 1, but number 1 does not depend on 2 back. And that kind of asymmetric function of dependencies in there can be encoded in a single supervisor, which keeps you from creating large chains of them. So one of the questions that easily comes after that is, why does restarting work? It's easy to see that if I have a bug in my voting mechanism on the one-for-all strategy, it's not going to make sense to restart. It's just going to crash hard and hard and hard. So the thing I want to introduce there is the difference between Heisenbugs and Bohr bugs. And those are terms that have been coined, I believe, by Jim Gray in '85 in the Tandem Computers paper, Why Computer Systems Fail and What Can We Do About It, which is a great paper that I recommend people read. Tandem computers have great apocryphal stories in building the most reliable systems of their eras. I think one of them is that one of their customers calls in a panic and tells them a car just drove through the wall of our computer room and knocked the computer over. We need help. I'm like, okay, we're gonna bring pieces and everything. Just tell us, like, how's the thing? No, we don't need pieces. The computer is still running. You just want to know if it's safe to tilt it back up now. And so they were extremely reliable for the time. The idea of a Bohr bug is that it's easy to reproduce. It happens all the time. You look at it, it's easy to think about. The Heisenbugs are the transient faults that happens once in 1,000, once in 1,000,000, once in 1,000,000,000,000 executions. And they're really, really hard to trigger on their own. And so while you're doing development and testing locally in development, the repeatable bugs and core features are super easy to find because you're putting all your attention into that. You don't want to ship broken systems. They're repeatable on a critical path. You're going to do all of that. If you're working on secondary features, you have a bit of different experience because everyone has this idea of diminishing returns. Extracting all the bugs of a code base is more and more expensive as time goes, in terms of fixing them, but also in terms of identifying them. And as you test, you're going to go in secondary features, and you're going to pay maybe more lip service to it than actually caring the same way you do about the core features. You're going to look at them, you're going to go, okay, I think we got decent coverage, it's good enough, we can fix them in the next release. Transient bugs, on the other hand, never happen, or almost never happen in development. And if they do, you're going to have a very hard time to figuring out what was wrong. You're going to blame, I don't know, space particles flipping bits in memory, and then you're not going to think about it anymore. But the thing is, if they require a 1 in a million execution to be triggered, it's going to be really, really hard to do it in a test case, especially if the test case always exercises the same path. Unsurprisingly, that has impact in the kind of bugs we find in production. The easy repeatable bugs in core features should never happen in production. If they do, you've shipped a broken product, you just failed. A secondary feature is going to happen pretty often. It's going to be that code path you don't see that much of. It's going to fail here and there. Those are going to be the first patches you're going to do. It's really, really rare that you get the core features and repeatable bugs in there. The transient bugs are going to happen all the time, especially if you work with a large system under load. If you're doing 100,000 requests a second, a 1 in a million bugs happens every 10 seconds in your system. And if you have, your systems is based on 10 nodes having 10,000 requests a second each, then something close to every 10 minutes you're going to have each of your nodes die. And that's going to be all the freaking time, even if it's just probabilistic. And of course, that's related to that one. Because the secondary feature is going to happen pretty often because we overlook them. The core feature should not happen because they're easy to find. And the transient bugs are going to happen all the time because we have no great way to reproduce them in development, aside from more formal methods or statistical analysis and better tooling, which we're apparently not willing to use as an industry. And so the bugs that are handled by restarts then, core feature is repeatable. No, you cannot fix these bugs. You're required to fix code. They're happening all the time. Your product is broken. Secondary feature is a bit of a maybe, it depends, right? Some secondary features are used by people as if they were primary features. If I'm exporting my, I don't know, expense report into a JSON in UTF-7, but I really, really care about that, then it's going to be a core feature for me, and restarting is not going to save me. If the poke feature on Facebook is broken and I restart and it works after that, it doesn't matter. It's still good. Transient features are pretty much always fixed by restarting, by the simple virtue that they require that complex interleaving either on multiple schedulers, multiple cores, or even latency on the network on services that you consume to be able to trigger them. And so by restarting, most of the time I'm going to be able to handle their failure and stop it from happening fine without a problem. So that's good, right? It's not a Heisenbug. We took care of that just by restarting. Every time I went online and discussed that on forums and everything, there's someone asking a question like that, and I really like that one by forum user Notorious BSD, asking, I like statically typed languages, and I restart my daemon after unhandled exceptions. What is Erlang going to win me on fault tolerance? And this is a great question. Yes, you can just restart your stuff and go on with your life. And that's true, it will handle a bunch of them. But to really gain the insights, I think it's interesting to look into the structure of a full program. And here, this is The idea of having a thing that counts votes in an election in Canada to figure out if Justin Trudeau wins again or something. So you've got the root supervisor. The supervisors are the rounded squares that you have. The first supervisor that I'm going to start is going to be the tally supervisor on the left. The tally supervisor is going to boot the storage supervisor, which is going to start the worker pool supervisor, which is going to start the pool workers. And once that's done, it goes back up, starts the cache, and then I'm able to start booting the districts. And it's possible that my pool workers have a one-for-one supervision, but my worker pool in the cache have a rest-for-one because the cache cannot work without the database and blah, blah, blah. Or maybe it's entirely different. It doesn't really matter at this point. District supervision is the same. It's really possible that as I boot the Quebec district, I start with the count of the process, and that one is really kind of critical. It's going to count what I have in a ballot box in terms of yes, no, abstention, for example. And then it starts a sibling OCR process that's going to read the ballots if I really wanted to do something that way. And reading the ballots in Erlang is kind of a tricky thing. There's a bunch of C libraries to do that, so I'm going to start a C process to do it and link it to that one. So the failures in C code don't take down my node, they only take down that process. I'm able to isolate the failures of C libraries by doing that kind of thing. And what I'm going to do is that every time a reading is complete, I send it to the count process that accrues them. And when I'm done with a ballot box, it stores in a database by contacting a worker pool. Or maybe it publishes that into a Kafka stream. Or it does anything you want. Maybe it dumps it to a file. We don't really care. That's clicking a whole lot. And so that structure is encoded that way. And what happens with failures is that if, for example, the OCR process fails too often, there's a threshold after which my supervisor gives up. And the Quebec supervisor dies, I kill the count process, and then it's up to the district supervisor to start it over again. And so what I'm defining in there is a sequence of failures. When it's too often, I take down the system. Of course, when a district is up and running, I can start running maybe the live report subsystems, which is going to handle web sessions, have a web servers, and web workers. And what's interesting is that that one implicitly depends on the storage system to be there in order to function, because it's reporting the results from the web system. But the storage system does not rely on the web server to be healthy. And that's one of the things that's being encoded in that supervision tree that you don't see by just restarting a daemon. I've created an asymmetric relationship between the dependencies of my code. If I require the database workers to be present to work, it doesn't mean that the database workers require the web workers to be there. If I kill everything at once, I basically say that all faults are equal in my system. And this is not necessarily true. And what I have by the structure of supervision trees is a way to really define how the system boots, how it shuts down, but also all kinds of partial states of failure that are acceptable in there. And so there's going to be a bunch of strategies that I can have. As I said, if I put the connection opening in that one, I'm saying that the worker is going to be there. If I do it differently, I say it's not going to be available. I can have connections die or not. Maybe it's not expected. So for example, if I'm doing audit logging on financial data, I might easily say that the information I have in that one needs to be there all the time. And if the process for audit logging is not up, I want my system never to boot, because it's simpler to do that and be legally right than being legally wrong and then having to prove in court that blah, 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 you actually don't lose data, it's just a weird structure. And if I'm talking to a cache, Memcache, Redis, something like that, Kafka Boss publishing, it's very possible that I don't need the connection to be there. In fact, I have to expect that it's going to be broken. And so what's interesting is that by the structure, I'm also able to say if I'm working in a microservice architecture, I'm able to define all the dependencies I have to be able to boot. I require the availability of this service, of this service, of this service, but not these ones. And if some of them are there or not there, I might cause or trigger the entire failure of a system, or maybe not. But this is something I'm now able to encode in my system through the supervision structure. And in fact, if we look at all the supervision trees I've given you there, this really looks like, oh, this could be a database client, and that thing right there could really be a district application. And the live reporting thing is an entirely different thing, and maybe could even live in a different node. And in Erlang, you take these subtrees, and they're called OTP applications. Those are the libraries you have. Your libraries in an Erlang systems is just different supervision trees that you can have. And you're going to define through their dependencies whether a given sub-application, let's say the database, is a dependency of the tally app or the report app. So the thing I'm going to be able to do with that is say, for example, that the report app depends on the database for storage, but does not depend on the tally application. They are actually independent within the subsystem. And I can encode the dependencies, yes, locally within the same virtual machine. I don't need to run my microservices on multiple nodes. Given I'm in OTP, I can even upgrade them independently while the system runs. Of course, if you want to break them out, you're fine to do that, and you're still able to encode the same thing. It's just going to be that the storage app is going to run on both instances with their own dependencies. But that's been super critical to encode everything we have in that structure. And just by picking up how we boot the system, what we have defined within that framework with the components we have is what is critical or not to my system in itself. What is allowed to fail or not? If something is allowed to fail, I'm going to be fine. The OCR process is allowed maybe 1,000 times more failure than the database, or being able to actually store the count of a tally. I'm defining how the software should boot according to which guarantees I have, what is a critical subcomponents or not again. How it should fail again, meaning what are the legal states of partial failure. So I can say yes, it's going to fail by shutting down this in that order, but I'm also specifying that if the entire database subtree is going down, it's impossible for me to actually serve web requests. And if I encode my supervision tree differently, maybe I'm supporting that. But the structure I give my program at boot time, when I build it the first time, already takes care, or at least consideration, of all these possible failure cases. It tells me again once it's how it's upgraded, because you can do live code upgrades, even though a lot of people don't use these features. And the other thing that I have is a really, really good way to figure out which components depend on what through the application process. Because if I don't specify my dependencies right, the system will boot kind of wonky, won't work super well, but it becomes really, really easy to have a kind of graph of what depends on what in any one of the services you will be running. And so hopefully that will let me sleep at night. Hopefully, maybe not. That little image is one I really liked. I'm at Heroku, and I work on a team that does a lot of HTTP proxying and everything like that. And about 2 years ago, we replaced our entire instances and implementation of HTTP routing without telling anyone. And mostly we did that over the course of a few months, and after 3 months, one of the engineers on our team got a really, really expensive bill in one of our monitoring systems, because apparently for like $3,000 of bandwidth and too many errors were being sent in there, and we were not looking at them. The system was working fine, the tests were running, no customer was complaining. And what we found is that we were generating something between 500,000 and 1,200,000 exceptions a day on Heisenbugs having to do with the termination of connections that we had. And if this is something that we're handling, I don't know, 100,000, 200,000 connections a second over the entire system, it meant they were once in a 20,000, once in 40,000 bugs or something like that. And the thing is that because we were able to just restart and handle the case, we actually didn't need to care about it. The reason we fixed it is because it was too expensive on our coworker's credit card to handle that stuff. You can see that at some point we optimize, and you have that little blue line at the bottom in there. This is a baseline of exceptions that we know what they are, we know how to trigger them. They're not happening a whole lot of time, but they're not expensive enough on the billing at the end for us to fix. We've just decided to actually mute the exceptions and let them fail. We don't care about it. We know how it happens, we know it doesn't hurt, we just restart and keep moving. It's not worth our time to fix these ones, actually. Even though you have these systems, you have to expect failure. And I've been in a flight on a plane to Vancouver a few years ago where a hydraulic line broke, and we landed safely because they had 2 failovers. We only had a bunch of firemen looking at the plane to make sure nothing would catch fire. Now, the plane in the picture is not that one. This is the United Flight 734 from January or February earlier this year. The eastern seaboard of the US was being buried under, I believe, 24 inches of snow, and we were landing in Chicago. And the plane went fine, no problem with the plane. But as we landed, there was ice and snow on the runway, and we just heard that loud noise, which I believe is the equivalent of the ABS braking of the plane, and went off the runway into the grass. Oops. The plane is fine. It was not the problems of the plane, it was weather, it was the pilot, it was whoever like that. And the thing that happens is, even though the plane is that super reliable system, we still get really weird issues from time to time. And this is a diagram I took from not a security, but resiliency researcher called Richard Cook. He's working in life-critical systems and the healthcare industry, and if you want to go look at his videos on YouTube, they're all very, very good. This is almost stolen directly from one of his presentations. And what we have is generally this kind of principle of a laid-back, comfortable area and a danger zone, which is the margin of error before the failure of a system. And what we have in the laid-back area is everything running smoothly within the known parameters of what is acceptable. And as you work, you get pressure, for example, from the product, from customers, from load, from financial incentives, from marketing, for all kinds of departments, and even within yourself, to move the operating boundary closer and closer to the margin of error. And the thing that happens is that over time, we're going to get into that first little dot there. We're going to, ooh, we're in the margin of error. And then you come back and you say, oh, nothing went wrong. And so you're just towing the line and getting closer, closer every day to that incident boundary where everything explodes. But because you get used to operating within the margin of error in the danger zone, you usually normalize on that, and that becomes your new comfort zone on that line. And that's a tricky thing, because being in the margin of errors is something we should definitely respect in terms of operating guidelines and principles, because this is basically the buffer space we have when stuff starts being not good enough, and that's the time we have to fix it. And as we operate closer and closer to the margin of error, we basically lose all the flexibility we have in keeping the systems up, regardless of what structure they had in terms of supervision trees and stuff like that. And these practices are fully encoded and maintained by the personnel, the operators, the people working with the system, looking at diagrams, at metrics, and handling that. And that is a critical part of reliability. Like, we can mention fault-tolerant systems all we want in terms of supervision trees and fancy applications and fancy architecture and fancy analysis, but if you don't take care of really well-defining your operating boundaries, respecting that, and taking corrective action when you're closer to the edge, you're going to get nothing good. And so in the case of the airline industry, even though the plane went fine, they were prepared for failure. And what we count there is something like 1 fire truck, 2 fire trucks. There's a bus right there to carry people over. Cop car, people with lights to guide you around. Parts of the airlines that were being shut, and then tickets being reimbursed. And the entire system is made for that. There's this really important black card. I don't know what it does, but I'm super sure it's really important. But really, everyone was safe and sound on the flight. I don't know what happened with that. There was a lot of media about it for a short period of time. But really, I think this is what I would call the Zen of Erlang in a nutshell. It would really be about figuring out how the components you have interact, being able to figure out what is that error kernel that cannot be allowed to fail, figuring out what needs to fail together, what are the dependencies you have within a system and without the system at the external sides of it. And then by using the fail-fast mechanisms of links, monitors, and in the case of bigger frameworks like OTP and what you get into Akka, the supervision structures and the applications that you can divide from there to figure out really what is the worst case and how to recuperate from that. And I guess that's the Zen of Erlang. If you build by the interactions first, and you make sure that the worst that can happen is still okay and possible to handle, there will be very, very few faults or failures, even those you do not expect, that will make you very nervous, and you can sit back and relax. So that's about it for the presentations. Any questions or comments or discussions? All right, nothing. Thank you.